Here's some help with question 17 of Chapter 6-1, Sapling Learning Problem Set. So this question says, what is the silver ion concentration in a solution prepared by mixing 437 milliliters of a 0.357 molar silver nitrate solution with 389 milliliters of a 0.62 molar sodium carbonate solution? And they tell us that the KSP of silver carbonate is 8.1 times 10 to the minus 12th. So that's a very small number, so that tells us that silver carbonate is not very soluble. So if silver ions and carbonate ions in solution come close together, it's likely that they're going to precipitate. Actually, it's very likely that they're going to precipitate. So what we're told here is that we've got a silver nitrate solution, and you might need to know the formulas of these two substances based on the name, right? So here they are, silver nitrate and sodium carbonate, and we're told the volumes and the molarities. Now in the hints section, they suggest that you need to find the limiting reagent. So the limiting reagent, well, that implies that there's some sort of chemical reaction. And so the chemical reaction that's going on here is the reaction between the silver in the silver nitrate and the carbonate in the sodium carbonate. Now the nitrate and the sodium make these compounds soluble, but they in fact don't participate in the reaction. Again, they're what we call spectator ions. So this is the reaction right here that we're considering, the reaction between silver and carbonate to make Ag2CO3. We need the Ag2 to balance out the charges, so that means we're going to need 2 moles of silver ion for every 1 mole of carbonate ion that we have in the solution. So that's the limiting reagent problem that we're going to be solving. So the reaction, the balanced reaction, says that we need 2 moles of silver ion for every 1 mole of carbonate. So do we in fact have that? Do we have less than that? Do we have more than we need? So that's what we need to figure out to determine the limiting reagent. So let's first calculate how many moles of silver ion we have. And we can do that given this bit of information up here, the volume and the molarity. So the volume in liters is 0.437 liters, and the molarity tells us that we have 0.357 moles of silver nitrate. Now for every 1 mole of silver nitrate, you get 1 mole of silver cation, so I'm just going to use that stoichiometry right from the get-go. So 0.357 moles of silver for every 1 liter of silver nitrate solution. So this lets us calculate the moles of silver ion that we have. We can do a similar thing to calculate the moles of carbonate ion, CO3 2-. So in that case, we've got, or at least in my problem, 389 milliliters, that's 0.389 liters, times the molarity of the sodium carbonate, so 0.462 moles of sodium carbonate. Now from the formula we see that we've got 1 mole of carbonate in every 1 mole of sodium carbonate, so I can just use the same molarities. That's 0.462 moles of carbonate ion in that solution for every 1 liter of that sodium carbonate solution. And so I can use that to find the moles of carbonate. And then what I can do is just compare these two numbers and ask the question, do I have twice as many moles of silver as carbonate? If I do, then carbonate is the limiting reagent. If I don't, then silver is the limiting reagent. And so that's what we will use to determine the limiting reagent. And then what we're going to do is assume, because the KSP is really small, we're going to assume that essentially all of the limiting reagent is consumed. And so that's going to leave behind excess reagent of the other, leaving behind the excess reagent. And so then what we're going to need to do is figure out the concentration of the excess reagent. So that will either be the silver or the carbonate, depending on what you determined above. So whichever one is not the limiting reagent is the excess reagent. So we need to figure out the concentration of the excess reagent. And so that's going to be the moles of excess reagent. And I'm going to abbreviate reagent just R, so moles of excess R, divided by the total liters of the solution that we have. So if we think about it, the total liters of the solution, we have mixed these two volumes together, so we've now got a bigger volume, right? So we've mixed 437 milliliters of this solution with 389 milliliters of that solution. So we're going to have to add those two up. So 0.437 liters plus 0.389 liters, in my case, will give us the total liters of solution. Now we need to figure out what our excess moles of reagent are to calculate the concentration of the excess reagent. So moles of excess reagent, well, we can figure that out by subtraction. So if we know how many moles we started with, moles of R initially, INIT abbreviated, so moles initially, and we can figure that out because whichever one of these is our excess reagent, silver or carbonate, we've calculated what those moles are. So we'll know the number of moles of the excess reagent that we started with initially. So that goes here. And then we need to subtract off the moles of R that in fact reacted. Okay? Now, to figure this out, we're going to have to do yet another calculation. So this is a complicated problem because we have so many calculations. So let's go ahead and calculate moles of R reacted. Okay, so to do that, you're going to take your moles of limiting reagent, so I'm going to abbreviate that LR, so moles of limiting reagent, and you're going to calculate, using the molarity, the number of moles of limiting reagent that you started out with, and actually it's going to be one of these numbers up here that we've already calculated. Okay, so this will be molarity, moles of limiting reagent. Oops. So no, we want to figure out the oh, wait. Sorry. Scratch that. So moles of limiting reagent reacted. So moles of limiting reagent, we know that. So we need to find the moles of R reacted. So this we know from this calculation up here. So whichever one of these is our limiting reactant, we've already calculated that, right? It's one of these two numbers, these two blank spaces right here that I just circled. Okay, so we know that. Now what we need to do is figure out the moles of R that have reacted. So we can use the stoichiometry to do that. So up here we were told, for example, let's say that our limiting reactant was silver. So if the limiting reactant is silver, and it may or may not be for your particular problem, so this is just an example. So if the limiting reactant is silver, then we would take our moles of silver cation and we would multiply that by the reaction stoichiometry. So the reaction back up here tells us that there are 2 moles of silver for every 1 mole of carbonate. So this tells us that there is 1 mole of carbonate that reacts for every 2 moles of silver plus that reacted. Now, if your limiting reagent was moles of carbonate, you would simply have the same ratio but flipped over, and that will tell you how many moles of carbonate reacted. And that's the number that we're going to need to plug into this space right here. So if our excess reagent is carbonate, we've just calculated the moles of carbonate that reacted. All right, so this is how you're going to get moles of excess. All right, so we got several steps here. We got to get moles of carbonate, that gets plugged in here. Then by subtracting, you get moles of excess reagent, which gets plugged in here. And then you calculate the concentration of the excess reagent. Wow, we've done a lot of work, but it's going to disappoint you to learn that we still are not done. So we are asked to find what is the silver ion concentration. So you might think it's 0 because we made the assumption that all of the limiting reagent is consumed. So if silver was the limiting reagent, maybe it got completely consumed. So what we're going to do now is we're going to solve a solubility product constant problem. So we've got silver carbonate in our solution. We've got silver carbonate solid that has precipitated from this reaction. And so what we imagine is that some of this is going to break up to reform a little bit of silver and a little bit of carbonate in our solution. So this is how we will get a little bit of that substance out. And so we're going to use our KSP value here. All right, so now what we need to do is solve the KSP equation for the silver ion concentration. All right, so we know KSP. So one of these two concentrations we will have just calculated from up here. So this bit right here that I'm circling, the concentration of the excess reagent will be one of these. So probably the way this problem is set up, it's probably going to be that one. So that's going to be the concentration of our excess reagent. We'll plug in there. And since we know that, all we need to do is solve this equation for the silver ion concentration. So at the end of the day, we're figuring out what the silver ion concentration is here. So you just solve this equation like we've done before for the silver ion concentration. So it would be KSP divided by the carbonate ion concentration, which we may have had to work hard to calculate, and then we're going to take the square root of both sides of this equation because it's squared up here in this term. And plugging in numbers, that should finally give you the silver ion concentration, which is the answer to the problem. And again, where did that silver ion come from? Well, first, the silver and the carbonate reacted to make some solid, and then a little bit of this solid will, and so we're going to consume essentially all of whatever the limiting reagent is, but a little tiny bit of this solid will redissolve according to our solubility product constant. And so that's going to give us a little bit of silver in our solution. So that's question 17.